Hello everyone, welcome back to my channel. So we were studying statistics for AI and data science. Today we are going to study cumulative distribution function. So let's start. We have learned about the probability density function of a Gaussian distribution in the last session. Today we will learn about the cumulative distribution function. Fine. We saw how to construct a cumulative distribution function from PDF when we learned about exploratory data analysis on day 9, right? Those of you who have not watched my exploratory data analysis playlist, I will attach the link of the playlist in the description. This is how my PDF looks like. We saw this in the last session. CDF of my Gaussian distribution looks exactly like this. So if X is my random variable, we do know that CDFs always range between 0 and 1. The left bottom is always at 0 and the right top is always at 1. To understand better, let's take our blue curve here. Blue curve here is a Gaussian or a normal distribution. So since we know X is a random variable, so we can write it as X belongs to normal distribution with mu and sigma square. Here, mu corresponds to 0 and sigma square corresponds to 0.2. We can see here mu is 0 and sigma square is 0.2. And what is the sigma square? Sigma square is my variance. Now for this curve, this blue curve, given any point, let's take this point. This point is 0.8. So I'm taking this point and the corresponding point on this axis is, let's say this is 0.5. This is my 0.5. Fine. So given any point, what does CDF height represent? So here it represents the probability that my random variable X is less than equal to 0.5. So the height of my CDF tells me what is the probability that my random variable X takes value which are less than equal to 0.5, and that will be 0.8. Fine. This is my point and this is 0.5. Fine. So that's what CDF tells us about. So the CDF of a random variable which follows Gaussian distribution looks like this S-shaped curve. This is also very well recognized shape. But here are a few interesting things. If the mean of the random variable is 0, this is where the central point lies. Because our distribution is symmetric, which means that 50% of the point lies on one side of the mean and 50% of the point lies on other side of the mean, right? So the value corresponding to this 0.5 here, this point is at 0.5. So this is at 0.5. So the value corresponding to this half or 0.5 here will be at 0, at this point 0 for all these three curves, because all of them have a mean of 0. Fine. But for a green curve which has a mu of -2 and whose central point is at this point corresponding to 0.5. So here half on the y-axis corresponds to X is equal to -2 here. So for these three distributions, the mu is at 0. The corresponding value in the CDF will be at half, that is 0.5, correct? Because as you can see here from our probability density function that it's symmetric, which means half of the point lies on one side and half of the point lies on the other side. Fine. Having said that, the other important thing to note is variance. Let's say for this blue curve, the variance is this much. For this red curve, the variance is this much. And for this yellow curve, the variance is this much. Similarly, on this side also, for this blue curve, the variance is this much. For this red curve, the variance is this much. And for this yellow curve, the variance is this much. So you can see that the variance of the blue curve is smaller than the variance of the red curve. And the variance of the red curve is smaller than the variance of the yellow curve. So as variance is smaller, the CDF line for Gaussian distribution gets more and more closer to this line. This is my central line. As variance is smaller, this CDF line for Gaussian distribution gets more and more closer to this line, this y-axis lines. So if you look at this red curve here, it's slightly farther away from my x equal to 0. This is x is equal to 0 means my y-axis line. So this line is basically my x is equal to 0 line. So it goes farther and farther away. So this yellow line has much higher variance. So the CDF actually goes farther and farther away from this line as the variance increases. That's one of the important lessons of CDF. There is of course a closed form equation. We saw the equation for PDF of a Gaussian random variable. This is the equation of PDF of a Gaussian random variable. There is an equivalent formula for CDF. So this is the formula. You can see this is the formula for CDF and this is the formula for PDF. Correct. So you can see here in this nice table. So what the equation of PDF is and what is the equation of CDF is. I have taken this from the Wikipedia. Okay, having said this, there is another concept which is extremely important with Gaussian random distribution. This is called 68, 95, 99.7 rule. So you can find this nice diagram in the standard deviation page of Wikipedia. I have taken from there only. Let's assume somebody gives me a random variable x which is distributed normally or follows Gaussian distribution. Let's assume I am given mean which is mu and sigma square which is variance. So let's say somebody tells me that my mu is let's say 0 and my sigma square which is variance is 4. If my sigma square is 4, which means my sigma is if my sigma square is equal to 4, which means my sigma is equal to 2, which means, and this is called standard deviation. We know that sigma is my standard deviation, which means my standard deviation is 2 here. Fine. Then I can tell you a lot of things about this random variable x using this 68, 95, 99.7% rule. Let's see. First of all, we do know that the Gaussian random variable is symmetric, which means 50% of the point lies on this side and 50% of the point lies on this side. This is clear. 50% of the points should lie on one side of the mean and 50% of the points should lie on other side of the mean. Mean equals to 0 here. So here, what is our first standard deviation? This is called the first standard deviation. My first standard deviation, that is 1 sigma is equal to 1 into, what is the value of sigma? Standard deviation, that means 2. So this is my first standard deviation is 2 here. So my random variable x, which has a mean of 0 and a variance of 4, between this 0 and this 2, or you can say my first standard deviation, I can find 34.1% of my points, which actually means if I actually sample data from my Gaussian random variable, I can find 34.1% of my points here. If we consider petal length or any similar measurement, it's important to note that they cannot be negative. So let's suppose we have a variable x that follows a Gaussian distribution with a mean of 0 and a variance of 4. Now, if I were to sample values from this distribution, I can confidently predict without conducting any actual experiments or observing samples that a significant portion of the observation will fall within the range of 0 to 2 away from the mean or equivalently between mean and the first standard deviation. This is my first standard deviation. So here our mean is 0 and our first standard deviation is 2, right? So 34.1% of points lies in this region. In other words, if x is normally distributed with a mean of 0 and a variance of 4, so sigma is equal to 2 here. Sigma is equal to 2 and my mean mu is equal to 0. Then between -1 and this +1 standard deviation, my standard deviation is 2. So between this -2 and this +2, I will find 68.2% of my points. So combining these two, we get 68.2% of my points. So just imagine if I know that height of a human follow Gaussian distribution, and if I have the mean and if I have the variance or the standard deviation of heights, I can tell you that 68.2% of humans have height between this number and this number. I can tell you that without actually measuring thousands or even hundreds of thousands of humans. Similarly, I can tell you that between -2 standard deviation and +2 standard deviation, there are 95% of my points. Similarly, between -3 standard deviation and +3 standard deviation, I can observe 99.7% of my points. Now let's understand the same thing in a different way. So let me put it in this way. Let's assume X represents the height of humans. Let's assume this is a Gaussian distributed with a mean of, let's say, 140 and a variance of 2 to 5. So if my mean, that is mu, is equal to 140 and variance is 2 to 5, so my standard deviation, that is sigma, is equal to 50. So this is my standard deviation. Suppose somebody gave me this after doing a lot of experiment by just seeing the human beings on the planet. So what I can quickly infer from that is this. Let's say 140 is my mean. So instead of this 0 here, I have 140 here as my mean value. Since 140 is my mean, so 140 plus 50, this is my first standard deviation. So how can I find out this value? 140 is my mean value. So 140 plus 15 is my first standard deviation, and 140 minus 15 is my first this standard deviation. So this is my 155 and this is my 125. Fine. So by looking at this, I can quickly tell you that 68.2%, this 68.2% have a height between 125 and 155, because this is 34.1% and this is 34.1%. Combining this gives me 68%. So 68.2%. So 68.2% human beings have a height between 125 and 155. Similarly, I can tell you that 95% of the human beings have a height between this and this. And what is the value of this? So this is, let's say, this is 140. So this is 140 minus 2 standard deviation, that is 30, and this is 140 plus 2 standard deviation, that is 30. So this value will come out to be 110 and this is 170, fine, which means 95% of my human beings lies between the height of 110 and 170. Similarly, I can tell you that 99% of the human beings lies between this standard deviation and this thing. So this is 140. This is 140 minus 3 standard deviation, that is minus 45, and this is 140 plus 3 standard deviation plus 45. So this thing will comes out to be 95. So this value is 95 and this will comes out to be let's say 185. This means that the 99.7% of human lie between the height of 95 and 185. But you get the gist of my idea, right? This is called 68, 95, 99.7 rule of Gaussian distribution. So this is very simple numbers that you can easily remember. I mean, after seeing this for so many times, I remember it almost by heart. So one standard deviation is 68, two standard deviation is 95, and three standard deviation is 99.7. Fine. This is all for the day. I have also recommended few resources to learn, so you can check my description section. That's all. Keep learning, keep smiling. See you in the next session.